Sup guys, welcome to today's show. So today we are gonna talk compilers. Coding a compiler might seem like a huge endeavor, too big to even begin. But using the technique that I'm gonna tell you about today, you will break everything up in small little pieces and you take one piece at a time and build on it. And that way you can achieve very interesting results. Today I'll be showing some code examples in different languages, in C and in Haskell, and possibly other languages as well. And but the biggest part of this episode is not about a specific language. It's about the general sense of creating a compiler and what steps that need to be taken and so forth. So, which are these steps? There are about 5 steps. The first thing is you need to code a lexer. And a lexer is basically a program or a part of a program which breaks your code up in tokens, in small little pieces, the smallest possible unit of the language at hand. So that's step number 1. Step number 2 is defining your grammar. So the grammar is basically the logic of your compiler, how it's going to parse the file basically, and the different constructs of that specific language, how everything fits together syntax-wise. When you have your grammar and your lexer, you can code a parser, which basically goes through the entire list of tokens and match it against your grammar, and creates an AST, an abstract syntax tree. And I'm going to give some examples later on how an AST looks. But basically the AST is what defines the entire flow of your program. When you have your AST, you can code your code generation or code generator. So basically a compiler, what is a compiler? Well, a compiler takes a higher level language and turn it into a lower level language. So for example, if you have a C file, you create an assembly file. And if you have an assembly file, you might compile it into machine code. This step or this process is called assembling, but it's basically the same as a compiler. And the compiler that I am writing or have written is actually an assembly compiler. So the code generation step is basically taking your C code, for example, and turn it into assembly. And then you're done. Sometimes if you have a more advanced compiler, you will have an additional step in between the parser and the code generator. And that is an intermediary language. I'm not sure about the spelling there, but so basically you can turn your AST into your own language of sorts. so you can apply additional logic to it and maybe take care of labels and I don't know, functions, classes, stuff like that, to make the code generator more advanced and increase its capabilities. This should be 3.5, by the way. So 4 or 5 steps. Does it still seem like a lot? Well, let me show you some examples. So if we begin with a lexer, let's take some C code, very simple C code. Let's do something like 5 plus 2. So if we're going to break this up into tokens, which is what a lexer does, we will, let's do a table. So we have, to the left we have the string, the code basically, and to the right we have the token, like so. And the first token in this case is the string int, and it is a keyword. So there are different types of tokens, and int, or rather, you can define it as a keyword, but if we're going to be more precise, this is a data type. So that's the first. Then we have a space, and in C language, spaces are not tokens. So we will skip that, and then we have the main, including the parentheses, I think. Shall we do that? No, let's do like this. There are no hard rules how to do this step, but you have to decide for yourself, basically. But this is only an example. So main, that is a function. Let's see. Yeah, let's do like that. And then we have the first parenthesis, and that is, let's say, a bracket. And same with this bracket. And this is also a token. Let's call it bracket. You will differentiate between open bracket and round brackets and so stuff, but I will make it a little bit simpler this time. Then we have return, and that is a keyword. Then we have the literal 5, which you can define different ways, but usually you would do something like a numeric constant. And then we have the plus, and that is a binary operator. And then we have the 2, which is a numeric constant. And the semicolon is also a token. And then we have the last bracket. So this is what C code looks like under the hood. There are data types and functions and brackets and numeric constant and so on and so forth. we break everything up in these tokens, and that is the lexer's job, just to make the tokens. Not at this point, we are not syntax checking at all. The only thing we are looking for are different tokens, and that's it. All right, so when we have tokenized or lexed the entire input file, the next step is to define our grammar. And I have an example of that on my Twitter for my assembly compiler that I've written. So let's copy this so we can see it a little bit clearer. So let's jump this out a little bit. I will explain this in a moment. Like so. And I would like to get this in the same column if possible. Something like this. All right, so what is this? This is a representation of the grammar for my assembly compiler, and it is written in Bacchus Nauer form. And it consists of different so-called production rules. So each line is a production rule. And we have these non-terminal symbols, which is to the left. And to the right we have terminal. Let me just double check. Yeah, on the right hand side we have both non-terminal and terminal. And what does it mean? Well, these are production rules which basically can be expanded. So a program consists of several of these. So it can be a header and then a procedure. So these brackets around means that this will be repeated. So we have for each procedure and for each program we have a header, and then we have several procedures, and then end of file. And what is a header? A header consists of a keyword and the end of line, and it can be several in a row. And what is a keyword? Keyword in this case can be either entry followed by a label, or, this means or, it can be bits followed by an integer. And then we keep expanding on each of these non-terminal production rules. So this defines the grammar. So this is how the general logic of the compiler should work. This should cover all the different cases that your file can handle. And it seems kind of like a lot in this case, but I started out with maybe 2 or 3 of those. And then I have added each time I created a new instruction and so on and so forth. So that is that step, defining your grammar. And then we come to this point where we code our parser. So basically we are parsing these tokens, our list of tokens, according to these production rules. So we take one at a time and make sure that we pair them together. So if we, for instance, see the move instruction token, we want to make sure that it's followed by a destination token, and then followed by a comma and a source token. And if not, we produce an error. And if it's okay, we continue. And that way we parse a little bit at a time until the entire code is parsed. And what is the output? The output is an abstract syntax tree. So if we use this code for this example as well, an AST in this case would probably look something like, first we have a program, and then we have a function declaration, main of type int, with potential arguments as well. And then we have a return statement. And then we go to the next level, because the return statement consists of an expression. And our expression is a binary operation plus. And the binary operation in turn has 2 arguments, left-hand side and right-hand side. And then we have maybe end of program or something. So it creates this tree where with the program containing all of these, and the function containing these. I should have jumped in here as well, and so on and so forth. So when we parse this thing, we are able to recurse basically into the different parts, and that way we can handle rather advanced statements. And when we have our AST, I'm going to skip the intermediary language, because you can define that in a lot of different ways, and depending on the languages you're handling. But the code generator in this case will take this AST and turn it into assembly code. So it will probably look something like move into ESP, EBP, and before that before that we push the stack pointer, we move into ESP our EBP, and if we're going to return 5 plus 2, we probably move into some register, the 5, and maybe into another register, the 2, and then we maybe add those two together, and we return it by moving it. It's already in the EX, so it's returned. But basically we create our assembly code, or depending on the application. So in my case, I'm coding an assembly compiler, an assembler. So my code generation is machine code instructions like this. But it's the same general principle. You tokenize with your lexer, you define your grammar, you create your AST by parsing your tokens according to your grammar, and then you do the code generation. So a few simple steps. And you should always start small. So for example, if you're coding a C compiler, start by creating a compiler, all these different steps, but only for this code. So only for a single main function with one line, which is a return statement. When you have every part working, you can create the next thing. And that might be this binary operation, that might be that you define some variable, and then you just increase one step at a time, all the time. And after a while, you have a working compiler. That's how I did with my compiler, which I'm going to show you in a little while. But first and today we are going to focus on this first step, coding a lexer. How do we code a lexer? And I'm going to show an example in Haskell, but don't worry too much about the language. I'm going to explain what you need to know to understand how to create a compiler. But this episode is not about language, so I will not explain the language specific stuff. Just enough to make you understand. And let's create a new file, compiler compiler.hs, and this is module main where, and I'm just gonna have an empty main function to begin with. This line defines the return type of the main, and that's always IO unit, which basically means it returns nothing. And I will just set this to printing some hello world for now. Let me just see that it's uploading correctly. Yes, it is. And I will open up this in the interpreter. Like so. Okay, so first of all, what kind of compiler we're going to write? Let's do the example with an assembly compiler, and let's limit it to only 2 lines of code. So we want to lex this code that we move into the AX register the number 5, and then we halt. So this is our job, to be able to divide this up in tokens. And the tokens will be the move, which is an of type instruction. Then I will have a space token, because I like to use a space token from the beginning and then just filter them out. So I have a separator between stuff. And then we have a register token. We have the comma token, the literal 5, which I call an int token. And on the next line is another instruction token. All right, so how do we do this? There are a lot of different ways to do this stuff, and I'm gonna create a small version of a parser, because there are advanced parsers in this language which are very nifty and which I use in my compiler. But to make things a little bit easier to understand, I will make this a little easier. So we create a type, a data type, which we will call a lexer, and it takes a type argument, a type parameter. So this is basically lexer A. If we were to show it in like TypeScript, it would be something like, let me see, type lexer, and no, not these. So this is a type parameter in the TypeScript, which can be any type. And it's the same syntax in C#, for example, and many other languages. But in Haskell, it's an A like this. So this could be like lexer int or lexer string, etc. And this will have a constructor, and it will contain one thing, which is a function, which I'll call run, and I'm gonna tell you why in a little while. So this is basically like a structure if we're gonna show it in C code. So let's say we have a struct called lexer, and we can't really contain a function because functions in C are not first-class citizens, but we can have a function pointer which is at least similar. So let's say that is a, I don't know, void let's see, and we do this to define a function pointer. So basically we have some structure with a function inside of it. And we need to define what return type this function has and what arguments it takes. And in Haskell that is defined like this. So we take a string as a parameter, an argument, and we want to return a tuple. So a tuple, for those of you who don't know, that is when you return several variables at a time. So we want to return something of type A and a string. So input is a string, output is something of type A, the thing we define here. It can be any variable type, and we get a string as well. And why this structure? Because we are going to, let's say we're going to parse this move AX5 line. So this is the string that we send to our run function. And we will parse this, and we want to return a token. So the A in this case will be a token. So let's say we parse this first thing here, move, and that is an, let's say, instruction token. So that is what we get back. And what string do we get back? Well, we have parsed those 3 characters. So we get back the unparsed rest of the string, which is a space AX5. And this is a very powerful technique because we parse this thing and we return the token that we want, and then we also return the rest of the string, the unparsed string. So then we can do this again. And this time we send the space AX5, the thing we get back here. And we run this thing and we get back a space token. And then we have AX5 left, and so on and so forth until we have parsed everything. And if we have some error here, so let's say we just have ABC AX. In that case, we will return just an error and nothing else. And that is usually we do this in Haskell by putting a maybe in front of this. And maybe is a data structure which has 2 possible types. It can either contain nothing, which is literally nothing, or it can contain something called just, and then we have a value as well. So in this case, for example, we will get a just and this, just to show that everything has worked. And if it fails, we will get nothing. And then we can decide if we want to error out or if we want to try with another parser. Because we will create small little functions, small little parsers, which one parser which will check for move, one for AX, and so on and so forth. And they give a lot of nothing until we hit the right thing or error out. So that is how this is supposed to work. So let's begin by creating a parser which parses one single character. and let's call it char. And the type of this will be char to lexer char. So this A turns into this char, which means that we want to get back a maybe char string. And that is how this is. This is how you define the parameters and the return type. So you can have like several of these input parameters, and you read this like the last thing after the last arrow. That is the return type, and all these other are parameters, arguments. So in our case, we just have a single char as an input, the char we're looking for, and we have a lexer char as an output. So let's call this thing that we're looking for x. And we want to create a lexer because we want to return a lexer char. And this contains a function which will get a string. So when we run this parser, it will take this string from the code here. And we want to check the first character of this string against this x. And we can do this by doing if x is equal to the head of s. So the head is the first character. And then what do we want to return? Well, we want to return just because in this case we are successful. And the A turns into this char right here. So let's return the x, which is the char that we sent. And we want to return the rest of the string. And the opposite of head is tail. So tail is everything but the first character. So we take the tail of s, and that means that we are returning the unparsed string. And if it's not the right character, we just return nothing. And this is the entire thing, and we don't need this dollar. The dollar is basically to avoid having a lot of parentheses, but in this case it's not necessary. So let's save this and let's reload this thing, and we get some warnings because head and tail might cause an error if the string is empty. But I don't care about that right now. So we can check the type of char, and we see that it expects a char and wanna return a lexer char. So let's check the type of char provided a character. So let's say we're looking for a C. And in this case, we will return a lexer char. And now we can use our run function to run this parser. And the output will be a function from string to maybe char string. So what we type here is what we are looking for. And now let's give this a string. So let's take the first line of the code. So move into AX5, I think it was. Yes. And in this case, it's going to check the first character if it's a C. So let's run this without the T. And the return nothing, because it's not a C. But if we are looking for an M, then we get the just M and the rest of the string. And then we can continue on and check the next thing. Maybe we check if the next one is a O, and then we can continue to parse one character at a time. But it's better to parse a string at a time. So let's implement that as well. So this will be a string to lexer string. And we will have an X, and we want to create a lexer which takes a string. And what do we want to do in this case? Well, this S can be like this whole line, and the string might only be a subset of this. So depending on how many characters we're looking for, we want to check if this string has that many characters. So let's begin by we can use the let keyword to create intermediary values. So let's define the length of the X. And let's define what we're looking for. We can call that, let's just call it str. And we want to take this many characters from this S. So we just say take len characters from S. So if this X is move, for example, we'll take the first 3 characters from this line, and we want to compare it to the move. So that's what we'll do. We can, instead of doing an if statement, we can do a case statement in this case. It's like a switch statement in C, basically. And what we want to check, we want to check, let's see, we want to check str if that is equal to, if str is equal to x, that is what we want to check. And if it is, so if we get a true back, what do we want to return? We want to return a just. And we want to return the str and the rest of the string. So let's create another intermediary variable. We can call this str prime, perhaps. And instead of take this many, we will drop this many, which is the opposite. So we will get the rest. So if we have parsed move, the str prime will contain this. So we return str and str prime. And if it's not true, we'll return nothing, just like before. Let's see if it compiles. Yes. So now we have a string function and we give it what we're looking for. We're looking for move. And we want to run this parser. And we want to give it the first line of the code. So move AX5. And what do we get back? We get back just move and then the rest of the string. But if we were to have something else here, maybe we have this next line, which was a halt instruction, then we get nothing back, and we need to try some other of our parsing functions. So when we are able to parse strings, we can create small little parsers. So let's say we want to create one which looks for move, for example. We can call this move, and this will be a lexer token, because a token is what we want to get back. We haven't defined token though, so let's define this as, let's see, either it's an instruction, and I will not differentiate between different instructions at this point. I will make this as simple as possible. And it can be a comma, or it can be an, let's see, literal int. So these are our tokens. And how do we create this move thing? Let's see. We want to return a lexer token. So move should be equal to a lexer. And a lexer takes string. And what do we want to do in this case? Maybe we can do something like this. We can use our string and say that we are looking for move. And this will return a lexer string. So we need to map this to a function. Let's call it f, where f is a function from, let's see, from lexer string to lexer token. So f has a lexer. And what do we want to do with that lexer? We want to run that lexer. And then we get a string to maybe string, and we want lexer token. So let's see. So we want to create a new lexer. which is the lexer token, and this will take an S, and we want to run our lexer with the S. Expected lexer token actual lexer string. So let's see. So what do we get back in this case when we run the lexer? We get a string to maybe, right, we can't really map. I think we will do this a little bit easier at this point because I don't want to create a lot of type class instances and stuff. So let's just say that this goes from a string to a lexer token, and we have an x, and that is equal to a new lexer, which takes a string, and let's do like we did before. We are looking for look is equal to move, len is equal to the length of look, str is equal to take len of s, str prime is equal to drop len of s, and the return value is equal to if str is equal to our input x, then we want to return a just instruction. In this case, that's our token and str prime, else nothing. And let's just copy this thing. I'm not making this very nice at this point, but just so we have something to look for. So I will change this to the halt instruction, and I'll call this halt and this halt. And what's it complaining about? Halt. I have a let. I need to return. Like so. Alright, let's see if it compiles. No. No. 63. Same problem here. We need to have an in and a ret. So basically, the in is what we return, and then the let, we define all the intermediary values. Alright, it compiled. So let's try this. We can do like we did before with the string, but this time we are checking against move. Maybe we don't need to have an argument at all. Do we? No, I don't think we do. Because we have the S and we know what we're looking for. So we can compare the str to look instead. And same down here. Let's remove this and we compare it to look. This seems a little bit better. So now we can just run. We run move against halt. Maybe we need to. No instance for show. Okay, we can show the token because in Haskell you need to do deriving stock show to be able to print the values. And in order to get this, we need to add a language extension, which you do with these language pragmas. Didn't I save? Alright, so let's try this again. We run move against halt, we get nothing. But if we run it against the move AX5, we get back our token and this. So in that way we can create these small little functions which each checks for one thing, and then we can combine all of these. So we first check for move, and then if we get a nothing, we check for the next one until we get a just. And then we do the same thing all over again with the string that we have left until the file is parsed, and then we have our list of tokens. I'm not gonna continue to create everything here. I just wanted to demonstrate how you can create a lexer. And you can do this in other languages like C as well, of course. But it's a little bit easier in a functional language, I think. And especially when we get to the parsing step, that's especially true. Right. So that's basically what I wanted to demonstrate today. So in the next episode of this series, we are gonna continue with the next step, which is defining our grammar and possibly also coding on the parser, which will take our list of tokens and our definition of the grammar and check it against each other, parse a file, and create an abstract syntax tree. So I hope you liked this episode. So in that case, please press the like button. You know I don't like asking for likes, but the YouTube algorithm works in a way that if you don't press the like button, it interprets it as if you hate the video. And then it will not be shown to a lot of people. So, do you hate this video? Otherwise, please like and subscribe if you haven't already. And thanks for watching, and thanks for today.